everyone, and welcome back to this series on financial mathematics. Today we're going to be continuing our exploration of some of the fundamental mechanisms associated to financial mathematics and discuss another type of interest, which is known as compounding interest. So last time we discussed a very basic principle of interest known as simple interest rates, which, keep in mind, only depends on the initial amount, sometimes called the principal, for which we're going to be denoting by S0. So even though you wait more and more, if you're using simple interest, the amount for which you accumulate on a daily basis actually only depends on the initial amount that you invested, not how much has accumulated over any specific period of time. So if we look at a numerical example of that, let's assume that we have a simple yearly interest rate of 12.4%. And again, let's assume that that is a yearly simple interest rate. And let's assume that the initial amount in your account was, let's say, $500. So how much is going to be in the account after some period of time t? So we can generally represent that as S of t is going to be equal to the initial amount plus the amount of interest that's going to be accumulated in that account over some time t. So that's going to be equal to, again, S0 times that simple interest rate IS times the amount of time t. Right? So keep in mind, this is our principal, and this is the amount of interest. So this is the interest accumulated on time, let's say, capital T in the interval 0 to lowercase t. Okay? And obviously we can factor out S0 from both of these terms to write it in an equivalent manner, and we can write that as instead as S0 times 1 plus IS times t. Right? So for our particular example, we have a simple interest rate of 0.124 and an initial principal amount of 500. So that means after, let's say, 9 months, let's say, so S9 twelfths, so that's 9 months as an example, we're going to have what? So that's going to be equal to 500 times 1 plus our interest rate, which is 0.124, but that's our yearly interest rate, and we want to see how much time has elapsed from 0 to 9 months, so we're just going to multiply that by 9 twelfths. All right, so keep in mind, this interest rate in that amount of time must be in the same exact unit. So this is a yearly interest rate, and that's 9 twelfths of a year. Right? So always make sure that they're in the same exact unit. And you can find that that's going to come out to approximately $546.50. Right? So let's take a more analytical look at this expression. So if we look at S of t, which is going to be equal to S of 0 plus S of 0 I of s times t, the only thing that's really changing in this equation is t. That is the variable in this expression. So that means this is just a number, and this is a fixed number as well, because the amount of money that we initially invest in our account is not changing. And let's assume that we're working under a fixed simple interest rate, so that's also going to be fixed. So this is pretty much like some number b plus some number m times t. Right? And this is, of course, equal to S of t. So this expression should look fairly familiar to you. This is just an equation of a line. So therefore, if we have a linear relationship with respect to s with the variable t, then what we have here is just a linear relationship, and hopefully m is going to be a positive number, because s of 0 should be a positive number, I of s should be a positive number. Therefore, this rate should look something like this. So this particular value there, that's just the initial amount, and then after some period of time t, we're going to have some amount in our account, S of t, right? And of course this ratio of rise over run, that's of course your m. Right? So simple interest rate accumulates things in a linear way. So that's one thing that we can see just from the analytical perspective of simple interest. Another thing that I want to mention that's extremely important, and this is going to be a big factor that's going to differentiate from compounding interest, is that for any time change So for any time change, let's say TB minus TA, let's assume B is greater than A, and let's assume that that's greater than 0. So for example, the difference between today and tomorrow, or today and next week, then the amount of money in the account, in particular the change in the amount of the account, in particular SB minus SA, will also be greater than 0, even if B minus A is really, really small, and of course positive. Right? So even if it's hourly or minutely or secondly or in some sense instantaneously, as long as that instant is has a time difference greater than 0, you're always going to have some change in the amount. And we can clearly see that from our linear relationship. That is, this curve does not have any gaps. So usually in the realm of calculus, this is usually what we refer to as a continuous AT curve, or a continuous accumulation curve, right? So that's some of the basic principles they need to understand when it comes to simple interest rates. Now let us take a look at compounding interest rates and how they differ from simple interest rates. So what exactly is compounding interest? Well, compounding interest only adds interest to the account at fixed points in time with time difference delta t is greater than or equal to 0. Emphasis on greater than or equal to 0. So it could be equal to 0. That would match in terms of, continuous compoundings when it comes to simple interest rates. But compounding interest, continuous, and simple interest will have a slight difference. And I'll make sure to show that difference momentarily. But in particular, the difference between compounding and simple is that compounding can have a time gap between the times when interest is added to the account. So as an example, let's assume that we again have $500 as our principal, and let's assume that interest is added to the account every year with an annual percentage rate of 27%. So what exactly will that look like? So if we draw a little timeline here, let's assume that this is our timeline. So this is going to be t is equal to 0. Let's assume that this corresponds to 1/12, 1 month, 2/12, 2 months, 3/12, 3 months. And then let's go all the way down to 11/12 and finally 1. So that's 1 year. Right? So according to compounding interest, we're only going to be adding money to the account when t is equal to 1. So if we look at the amount of money in our account, so at t is equal to 0, that's going to give us $500. But after 1/12 of a year, we're not going to be adding interest, so it's still going to be 500. It's still going to be 500, then it's going to be 500, then it's going to be 500. And then finally, at the instant t is equal to 1 and not any instant before, then it's going to be 500 plus our interest, capital I. Right? So how much will be in our account at t is equal to 1? So at t is equal to 1, S1, that's going to be equal to 500 times 1 plus our annual interest rate, which is going to be 0.27 or 27%, and that's going to come out to $635. But notice that at this particular point, that's the only time that S of t changes. So it goes 500, 500, 500, 500, 500, and then once we get up to here, then it jumps to 635. So technically, compounding interest, where the time it takes is not instantaneous, looks like a piecewise function. So that means what? So that means if we look at our curve, so let's assume that this is our t and this is our S of t curve, what you're actually going to see is you're going to have our S0 here. So this is going to be our S0. And then after 1, it's going to jump up. And then at 2, it's going to jump up again. And then at 3, it's going to jump up again, and so on. Right? So you're going to have this potential curve go through these particular points, right? Now, is this curve linear? I'll leave it to you to sort of explore that problem on your own, but definitely keep an open mind when you try to answer that particular problem. But it's going to be obvious once we actually start mapping down our functions, right? So how can we express this piecewise function in a more formal manner? So S of t is going to be equal to what? So it's obviously going to be equal to 500 as long as t belongs to the interval 0 to 1, and open parentheses on the 1 because at 1 it changes, but at 0 it is equal to 500. We found that it comes out to 635 when t belongs to the interval 1 to 2, not inclusive of 2. And one can find, if you multiply that by the interest again, what is that going to be? So S of 2 and 2.1, 2.2, 2.3, and so on, that's going to be equal to 635 times 1 plus 0.27 again, because it's still accumulating 27% more than what was there at time t is equal to 1, which was 635, and that's going to come out to approximately 806.45. So that's going to be equal to 806.45, and that's going to be true for t belonging to 2, 3 not inclusive, and we can continue that forever downwards unless we have a stopping point for which interest accumulates on the account. Right? So that's going to give us our piecewise function representation of this yearly compounding interest. So let's see if we can start building some mathematical formulas so that we can more formally analyze this particular financial structure. So we know that S1 is going to be equal to S0 times 1 plus our interest rate. So from this particular equation, we can say, okay, well, S2 is just going to be equal to S1 times 1 plus our interest rate. And keep in mind, these notations 1, 0, and 2, 1 are depending on the frequency for which I is compounded. So if I corresponds to a yearly interest rate, then that means 0 and 1 correspond to year 0 and year 1. And year 1 and 2 is just, the 1 year has passed, assuming that I is a yearly APR. But if I is a monthly compounded interest rate, then that means 0 corresponds to 0 months, then 1 month, 2 month, 3 month, and so on. Keep in mind those units must be in the same exact unit. Right? So if S2 is equal to S1 times 1 plus I, but keep in mind we already actually have an expression for S1, that's just S0 times 1 plus I. We can use that and replace that in the equation for S2, so S2 is going to be equal to S0 times 1 plus I, and then we have this 1 plus I that's sort of chilling there from our S2 equation, so we're going to have 1 plus I. And notice that we have two 1 plus I terms here, so we can write this as S2 will be equal to S0 times 1 plus I, the quantity squared. And we can repeat this process again. For example, S3 is going to be equal to S0 times 1 plus I to the power of 3. And we can continue this inductively, and we can find that after n accumulations of interest, we have that Sn will be equal to S0 times 1 plus I to the power of n. Now we have a bit of a mathematical framework. Now we can actually start using that to solve some real-world problems. Let's assume that our initial principal is $700, and let's assume that interest is added to the account at the beginning of every month with a monthly interest rate of 3.4%. So that means our balance is not going to increase every day, it's only going to increase every month. And let's also assume that t is equal to 0 corresponds to January 1st, 2024. How much will be in the account as of May 17th, 2026? So how much will be there? So let's sort of draw a timeline to sort of get a sense of what's going on here. So S0 is going to correspond to January 1st, 2024. And we're going to be accumulating interest in a monthly way, right? So for example, if this is S0, then we're going to have, that's going to be the beginning of January. So it's going to be February, March, April, May, June, July, August, September, October, November. And then December, that's going to be the next year. That's going to be S12, not S1, because these little tick marks is going to be monthly. That's when interest is going to be accumulated into our account. And then, of course, that's going to be January 1st of 2025. And we need to get to 2026. This is going to be 13. That's going to be February, March, April, May, June, July, August, September, October, November, and then finally December. And then it's going to come in January. So maybe I counted that right, maybe not. Who knows? So let's assume that that's going to be 24. So this is going to be equal to January 1st, 2026. And then it's going to be equal to January, then February, March, April, and May. right? So what is that going to be? So that's going to be 25, 26, 27, and 28. Keep in mind 29, that's going to be the next month after May, which is going to be June. Right, so that's going to be June of 2026. That's going to be the next time it's going to increase. But keep in mind, it does not increase over the span of this particular time. It's only going to jump up when t is equal to 29, and it was only going to be smaller from t is equal to 27 up to t is equal to 28. And keep in mind that is a open circle on that lower level. Right? So what we're interested in is May 17th, 2026. So that's going to be somewhere along that line, which is going to be the same exact value as t is equal to 28. So now we can use our mathematical structure for our financial product and then figure out how much or what is the height at this particular value. So that's going to be S28 in terms of what we're interested in. Okay, so what is S28 going to be equal to? So S28 will be equal to, from the structure that we've already previously derived, so that's going to be S0 times 1 plus I to the power of 28. Keep in mind, 28 corresponds to 28 months because I is framed from the perspective of monthly. So that's going to be equal to what? So that's going to be S0 times 1 plus our monthly interest rate, so 0.034 to the power of 28. But keep in mind that S0 was actually given to us. That was given to us to be $700 as our principal. And then after 28 months, i.e. between May and June 2026, we're going to have approximately 1,785 and 14. So that's going to be our balance in that particular interval of time. Right? Now, have you figured out whether this compounding interest is also a linear structure? You should be able to figure it out by now. So keep in mind, for simple interest rates, our structure was S of t is equal to S of 0 plus I of s times S of 0 times t. And keep in mind, we were able to prove that this was a linear growth because that's a number, and that's our variable of time. But for compounding, what exactly do we have here? So S of t is going to be equal to S of 0 times 1 plus I to the power of t. So t is going to be located here in the exponent, not at the base. And keep in mind, I is typically going to be greater than 0, so that means that base is going to be greater than 1, right? So this is a exponential growth of money. Therefore, in the long term, exponential growth is always going to be larger than linear growth if you wait long enough to do so. Right? So that's what we see when it comes to compounding interest. Now, let's actually take a different look at this particular formula and see if we can frame this from a different angle. So let's assume instead, so let's suppose that we have an annual percentage rate of 12.5%, but interest is compounded monthly. This is commonly how people will frame a financial product in terms of an annual percentage rate. Some people will do it monthly. So what would be our monthly interest rate? So our monthly interest rate in this particular case is going to be our annual percentage rate, which is 0.125, divided by 12, because there's 12 months inside of a year. Right? So if that is our particular interest rate, and let's assume that S0 was equal to, let's say, $220, how much will be in the account after, let's go with 2 years, which is the same as 24 months. Right? So if that is the case, then what are we going to have? So that means S, and let's put units in these subscripts since we're having a couple different times going on here. So S of 2 years, which is going to be equal to S of 24, is going to be equal to S0 times 1 plus our annual percentage rate. So our annual percentage rate, so APR, so our annual percentage rate divided by N, which is going to be equal to 12 for our case, to the power of 12 times t. Right? And you might be thinking, okay, why am I exactly writing it like this? Because didn't that used to be just t, and didn't that used to be just I? Yes, but it depends on the unit that you're framing things with respect to. So if you're interested in years, then what are you actually going to have? So that's going to be equal to our principal amount, 220, plus our annual percentage rate, which is 12.5%. And then we're going to be dividing that by 12. So this is going to be equal to our I, our monthly interest rate. And we're going 24 months, but keep in mind that's just going to be 2 years with 12 compoundings per year, right? Because 12 compoundings per year is just going to be 12 times 2, which is 24 months, which is just 24 monthly compoundings, right? And that's obviously going to come out to, let's say, 282.12. And you're like, okay, so I'm compounding interest monthly. Can I get more money if I were to compound money daily? Well, we can always check that and verify just to make sure. So what about compounding daily for 2 years? So what will that come out to? So again, we're still going to be looking at 2 years, but the only difference is we're going to take that 2 years and multiply by the number of days in that year. So technically this is going to be S of 730 days, and this is going to be 2 years. So keep in mind, make sure you're very clear on the unit that you're actually using for these subscripts. So what is that going to be? So if I want to frame it from the perspective of years, which I think is a little bit more easier to deal with, that's going to be equal to what? So that's going to be equal to our principal, S0, times 1 plus our annual interest rate, 0.125. But now we're going to be compounding 365 times per year, and we're going to do that for 2 years. So 365 times 2, that's going to be equivalent to your 730. And that's going to come out to approximately 282.47. So if you look at it, notice that it does increase in terms of the balance. But one could argue, well, it's only increased by approximately, 35 cents. Is that really a lot? It depends, because technically I'm charging you interest a lot more frequently. But, maybe people will not really realize that this is a lot of money, so maybe we can go a little bit more frequent, or as frequent as we can possibly get when it comes to our compoundings. Why not do like every single minute or every single second? Or why not just use calculus and be like, okay, is it possible that we can compound continuously? Right? So let's see if we can figure out what it would mean to compound continuously. So compounding continuously. So the number of compoundings is now going to be equal to an infinite quantity. Now there's going to be one little property that I'm just going to recall from calculus, and if you don't remember this, you can take this as axiomatic if you wish, and that is the limit as n goes to infinity of 1 plus 1 over n to the power of m. This is going to be equal to e. Some people define this limit to be equal to e, and that's going to be approximately equal to 2.71828 and so on. And if you're not familiar with this notation or notion of a limit, pretty much what we have here, if we define a function of n to be equal to this 1 plus 1 over n to the power of n, and we look at what happens as n gets really, really big, what you're actually going to see is that this function is going to increase starting from 1, but it's going to shallow off, and it's going to approach this horizontal asymptote, right? So what is this number that this function gets extremely, extremely close to as n gets really, really large? Well, it's going to get really, really close to this number e, which is sometimes called the base of the natural logarithm. So how can we use this mathematical fact to compound continuously? So if we continue with our example that we had before, let's assume we want to look at the amount of money in our account after 2 years, but we're going to be compounding instantaneously or continuously. So instead of daily, 365 times 2, it's going to be infinity times 2. So that's going to be equal to infinity times 2, which is infinity. Now, we enter this realm of what notation really is the best notation here, but what we're going to do is we're going to stay consistent and just focus on the 2 years. So in the realm of mathematics, what would that look like? So that's going to be our principal balance, and then it's going to be 1 plus our interest rate divided by the number of compoundings, and then it's the number of compoundings times the number of years that we're interested in compounding. But in this case, this is going to be equal to infinity and infinity, and you're like, well, what's that going to be? Now, I want to just mention one brief thing, just in case you're not comfortable with limits from calculus. One may argue that, you have 0.125 divided by infinity. That's going to be equal to 0, and 0 plus 1 is going to be 1. And then 1 to the infinity is going to be equal to 1, and then you're going to have 1 times 220, which is equal to 220. But that wouldn't make sense because we haven't made any money at all, and it definitely should be more than, $280 like we had with the daily or the monthly compoundings. So this approach to evaluating at infinity doesn't work, and you can't do that. So what we can do is use those tools from calculus. So again, recall that our problem is to figure out what is this limit as n goes to infinity of S0 times 1 plus our interest rate divided by n to the power of n times t. This is what we're interested in finding. Now, a couple things that you should be able to figure out, even if you haven't taken calculus. If we take n and send it to infinity, and we take n and divide it by r, where r is our interest rate, that's also going to go to infinity too, right? Because infinity divided by a finite number is still positive infinity. So what I'm actually going to do is I'm going to call this new variable n divided by r, I'm going to call that u. And if I rearrange this particular expression for n, I'm going to have that n is equal to u times r. And you might be thinking, why would I want to do something like this? So let's actually take a look at this limit and see what happens to it. So notice that as n goes to infinity, u is going to go to infinity too. So I can write that as u goes to infinity. And then we're going to have SO times 1 plus. So if n over r is equal to u, that means 1 over u equals r over m. Right? So that means this is just going to be 1 over u to the power, and n is just going to be equal to u times r. So we're going to have u times r, and then we still have that lonely little t next to it. Now, the next thing I want to sort of focus on is this little term right here. Notice that that's the 1 plus 1 over something to the power of something. That goes to e as that something goes to infinity. So we can use the properties of limits to sort of partition everything out that does not have u in it. For example, this rt doesn't have u in it. This s of 0 doesn't have u in it. So we can write this by sort of rearranging as s0 times the limit as u goes to infinity of 1 plus 1 over u to the power of u, and we have that power of rt located there. So by our properties of limits, we already know that that's just going to be equal to e. So that means this is just going to be equal to S0 times e to the power of rt. And we can actually just write that in a more simpler fashion as S0 times ERT. And keep in mind, some people will call S0 the principal, and some people will write it as PERT as well. But this is going to be the continuous compoundings after, t years. So now that we have this mathematical structure to work with, now we can find our answer for continuous compoundings for our example. So if we continue onwards, so after 2 years, that's going to be equal to 220 times e, and keep in mind e is approximately equal to 2.71828 if you don't have that button in your calculator, to the power of r, which is our annual percentage rate, which is going to be 0.125 times 2 years, and that's going to come out to approximately $282.49. So that's how much money you can accumulate in your account if the amount of interest is compounded every single instant of time. Every single instant of time. So that means, well, keep in mind this particular expression, st is equal to s0 times 1 plus I to the power of t. This was equal to an exponential rate. And also s of t is equal to s0 times e to the rt. This is also an exponential growth curve. The only difference is that this is a continuous curve, whereas the other one, for compoundings, what we had was a bunch of lines that sort of looked like this, right? Where these closed circles sort of accumulated in a exponential fashion. But keep in mind, these little curves didn't exist in our continuous compoundings because they have gaps. But for continuous compoundings, now we have a continuous curve. But it's an exponential continuous curve, not a linear curve, sort of like our simple interest rate. So if somebody asks you, okay, well, if continuous compoundings is continuous and simple interest is also continuous, is this going to be the same as simple interest? Obviously, since they're completely different curves, you should be able to say, no, of course not. One's a linear rate and one's an exponential rate. So if we look at our simple interest rate, how much money will we have in our account? So that's going to be equal to 220 plus our principal 220. Let's assume that our simple interest rate is 0.125, just as a basic rate. And then let's multiply that by 2. You can find that that's going to come out to $275, whereas our continuous came out to $282.49. Now, you may argue that, okay, 282 and 275 are not that large, but if you wait longer and longer and longer in terms of the amount of time for which you let that interest accumulate, you will see that this compounding interest, whether it be finite or continuous compoundings, will be extremely more significant in terms of its growth and its magnitude compared to your simple interest rate. So those are just some of the basics associated with compounded interest that you definitely should know and how they compare to simple interest rates. Hope you enjoyed the video, and I'll see you in the next one. Take care.